Hello and welcome to another tutorial in monitoring of forest resources. My name is Lutz Fährmann and this time I'm not alone. I brought two of my colleagues and they will explain today how a terrestrial laser scanner works. On the left hand side, my colleague from China, her name is Zhu, and left of her this is Edwine from Indonesia.
As Dr. Fährmann said, today we are going to introduce you about terrestrial laser scanning. A laser scanner can quickly and accurately measure the 3D environment and 3D reality by measuring the distance and the angles to the objects. And actually, a scanner can be carried by different platforms. Today we are going to focus on the terrestrial laser scanning, where the laser scanner is carried by a tripod on the ground. But how does a laser scanner record the 3D coordinates? Edwin, do you know it?
Yeah, I will try to explain it, yeah? So the terrestrial laser scanner here is a complicated device and carried a lot of sensors. And by measuring the distance and angle to the objects, it will produce the measurement as Sue said. And a laser beam here sent by the scanner here through the mirrors and get through the objects. And in our case here, the wavelength of the infrared beams is 905 nanometers. And when the beams hit the objects, it will reflect it again back to the sensors here, to the scanner. And the time difference between the emitting beams and the receiving beams will be used to measure the distance between the laser scanner and the object. And at the same time, the laser scanner will also, record the horizontal angle and the vertical angle through this mirror.
So the laser scanner can automatically combine the angles and the distance to make up the polar coordinates and then transform to 3D coordinates.
Exactly. That's what's so-called as point cloud.
Now I understand everything, and I'm so excited that we can start our small scanning project. And I think I would like to scan this tree. So I have to find my scanning position, which I can see the tree clearly. But the problem is from only one side, I can't really see the whole tree. And what can I do, Edwin?
Yeah, I think we can have multiple positions, yeah? Multiple scan positions, and we need it for registration. And for this registration, we need the overlapping area or the common points.
Speaking about common points, that's why we need those targets. And we can put those targets around the tree and we can use it for the registration. And I think it's really important when we have this homogeneous landscape, like in the forest or in the grassland, right?
Yeah, for sure. And we can even without the common points here, the target, we can use it also. It's like for indoors and for the objects that has special structure, for example, we can do it like that also.
Okay. Okay, so this is our scanning position and our target tree is behind us. Can we start already scanning?
Wait, I think first we need to do the weather check, whether it's appropriate for scanning. And yeah, I think today is not raining. And for the wind, it is advisable to have the wind speed less than 14 kilometers per hour. And also the temperature, I think temperature now is quite suitable. It's not too hot also. And we have to make sure that the battery is checked there and also the storage card is there. and we need to make sure that it's mounted on the leveled tripod here.
After the preparation, we can start to scan our trees. But before scanning, we also have to check some important parameters here. We have to first change some important parameters. For example, the project name, because we would like to assign all our scans in the same project. And we can change here. And then we can also change the resolution of the scan, like how precise you want your scan to be. And also we can change the angle of the scanning if you want to have a wide view of the scan. And I think we can also choose if you want to include those RGB information from the scan. And you can also change something more here. But now I think we are fine and we can start to scan already. Los geht's, Edwin.
Up, stop. Yeah, we must keep in mind that this laser device is categorized as 3R, which is hazardous to eye. So we should avoid looking directly into this mirror here and to the scanner. That's why sometimes we need some warning sign to avoid people to come and see directly to the scanner here.
Now everything is perfect. We can start scan. Okay, so the scanning is done, and the last part we have to try to figure out if our scan trees is completely on the screen, and that's all. We can move to our next scanning position. So now we are in our second position, and we have to make sure the bubble of the navel is also in the center in this position. After all the settings, now we can start to scan the tree again from the second position. Now we are back in the office and we can transfer the data from the scanner to our working computer, like here. As you can see here, there is a folder called Raw Scan. You can open it, and then we have to pay attention to the file with FLS extension here. We can also open it. In this FLS file, it includes all the data from one scan. Okay, let's find the software to open our data. Normally, a scanner owner would also have a paired software. They can open the raw scan. But if you don't have the paired software, don't worry. We can introduce you some alternatives. One of the options to open FLS file is Autodesk Recap. It's free for students, and you can use Autodesk Recap to convert scan file data into a more common format and for further processing using other softwares such as Cloud Compare. Since converting the data format is relatively easy to do in Autodesk Recap, so I will skip this step in this video. And here is already a scan from a former project. It has been already transferred into E57 format. Next, we can use Cloud Compare to visualize the scan and do some basic measurement. Cloud Compare is an open source software and it's very powerful. Now we can open the data. Okay, so here is our scan. and we can use the mouse to move it around like this, or we can zoom in and out. And of course we can change the properties of the scan. So we just choose the scan here, and now we can see this name of the scan and if it's visible. Also we can choose to see the scan with colors. Now it's with colors. And also you can see how many points are in one scan here. And also we can change the point size to make it bigger. Also in these viewing tools here, we can also change the perspective to view the scan. So here is from the top, from the front, or from the left side. Finally, we can do some basic measurement of the trees. I will show you how to roughly measure the single tree height and dBH. Firstly, we have to extract the single trees from the scan, and there are a lot of ways to automatically do that. But for the demonstration here, I will only manually crop out one sample tree to measure. I will use this tree here as our sample tree. To crop it out, it's very easy. We only have to select the point cloud here and use the segment tool here. We just choose the area of the sample tree and segment out. Yes. So you can see the original point cloud has been divided into two parts. And in this part here, we have our sample tree, but still some other points are left in this point cloud. And we can continue with the segmentation until we have only the points we need. After the manual extraction, we finally have our single tree here, and we are going to measure the tree height. Actually, we can have a rough idea about the tree height by checking the box dimensions here. So the vertical dimension is represented by Z, which means the highest point to the lowest point, and the tree height is around 26.7. Of course, we can manually picking up 2 points to measure the distance for the tree height. So we are going to use the tool here, point picking. And we are going to choose 2 points. The first can be the lowest point, and the second can be the highest point. And now we can see the distance between those 2 points, which is 26.4. So we can consider the tree height is 26.4. As for measuring dBH, one common method is to cut out a 20 centimeters long slice from the stem at 1.3 meters height, and next we will fit the slice as a cylinder. The diameter of the cylinder is considered to be the dBH of the sample tree. So let's cut out a slice from here. As you can see, the green line here means the 1.3 meters. So we will create the slice based on this green line. And we are going to use the function cross section here. Okay, so let's see, 20 centimeters. Perfect. So we can create a new cloud as the slice. And now we have the slice for measuring the dBH here. Next, we can create a cylinder based on the slice here. And we only choose the slice and use the shape detection function. So we choose the cylinder as a primitive, and the minimum support point can be 500. Okay. As you can see here, 2 cylinders were created. Let's look at those two cylinders here, and we're going to check the original point cloud. As you can see, the orange cylinder is unrealistic here, so we uncheck it, and the green one seems to fit better. So the radius of the green cylinder is around 25 centimeters, so the dBH of the tree is around 50 centimeters. If we are not satisfied with the result, what you could also do is to measure the dBH by yourself as the same function we use to measure the tree height. So we choose the top-down view and we choose the point picking here. Then we can just choose 2 points here to measure the distance, which is around 56.5. We can also take another measurement from different direction to average those two measurements. So another measurement, the result is 51.1. Then we can just average those two distances to have the dBH of the tree.